This is Dr. Willard Frank Libby, an American physical chemist. In 1960, he won the Nobel Prize in Chemistry for his work on radiocarbon dating, a process that revolutionized archaeology and paleontology. Our lesson for today is about the mathematics of carbon dating. A common complaint among math students is that they cannot see the application of mathematics in real life. In this week's episode of our live stream, our theme is math application. Let me start with the science of carbon dating first before we discuss the mathematics behind it. Cosmic rays enter the Earth's atmosphere in large numbers every day. For example, every person is hit by about 500,000 cosmic rays every hour. It is not uncommon for a cosmic ray to collide with an atom in the atmosphere, creating a secondary cosmic ray in the form of an energetic neutron, and for these energetic neutrons to collide with nitrogen atoms. When the neutron collides, a nitrogen-14 atom composed of 7 protons and 7 neutrons turns into a carbon-14 atom with 6 protons and 8 neutrons, and a hydrogen atom with 1 proton and 0 neutron. The carbon-14 atoms that cosmic rays create combine with oxygen to form carbon dioxide, which plants absorb naturally and incorporate into plant fibers by photosynthesis. The radioactive carbon will react with oxygen in the atmosphere to produce radioactive carbon dioxide. The radioactive carbon dioxide is breathed in and stored by plants, which are consumed by herbivores who are preyed on by carnivores or omnivores, such as humans. The carbon content of every organism under atmosphere, therefore, is composed of mostly C12 atoms and a minuscule number of C14 atoms. The organisms, while they do consume carbons, also expel it when they exhale. The transaction or the cycle of producing, consuming, and expelling C14 atoms occurs in a way that even though the amount of C12 and C14 atoms in the environment and in an organism may vary, their ratio will remain the same. This is the working principle of carbon dating. Despite the transactions, a living organism maintains the same ratio of C14 to C12 atoms as found in the environment. The ratio of normal carbon, C12, to carbon-14 in the air and in all living things at any given time is nearly constant. Around 1 in a trillion carbon atoms are carbon-14. At this moment, your body has a certain percentage of carbon-14 atoms in it, and all living plants and animals have the same percentage. As soon as a living organism dies, it stops taking in new carbon. The ratio of carbon-12 to carbon-14 at the moment of death is the same as every other living things. But carbon-14 decays and is not replaced. The carbon-14 decays with its half-life of 5,730 years, while the amount of carbon-12 remains constant in the sample. By looking at the ratio of carbon-12 to carbon-14 in the sample and comparing it to the ratio in a living organism, it is possible to determine mathematically the age of a formerly living thing fairly precisely. That is what we are going to do today. Let's start learning the mathematics behind carbon dating. Here is our problem. A paleontologist examining the bones of prehistoric animals estimates that they contain 2% as much carbon-14 as they would have contained when the animal was alive. How long did the animal live? If prior research points that the animal being around 20,000 years old, how much carbon-14 should be in the animal? So we can think of the situation this way. You have this bone containing 2% carbon-14 compared to what is expected when the animal is still alive. Here's the model of carbon-14 decay. At the moment of death, we are at this point. We have at time equals 0 year, we have 100% of the expected carbon-14 volume. Once the animal died, carbon-14 decay and its content is decreasing and decreasing. And after 5,730 years, half of the original content already decayed. So we are here at 50%. And then another 5,730 years passed, that is at 11,460 years, the original 50% is cut into 2, so we now have 25% left. Then another 5,730 years elapsed, and we will cut this 25% to 2 again to get about 12.5%. And then continue the process, and based on this graph, we can estimate that at around 50,000 years, most of the carbon-14 present in the animal at the point of death would have decayed already. So that's the limitation of this carbon dating. After 50,000 years, there would be very small amount of carbon-14 left in the fossil. Let's go back to our formula for continuous growth and decay. When you study exponential function, you come up with this equation. F of t is equal to ae raised to k times t. In this function, a is the initial amount, in our case, the initial amount of carbon-14 present at the time of death, and that's 100%. Then E is the natural number, which we already discussed in our previous video. K is a constant, and T is the independent variable, which is our input in the function. If K is positive, we have growth. If K is negative, we have decay. In the case of carbon-14 decay, with a half-life of 5,730 years, then we can substitute this 5,730 to the function to get this initial equation. F of 5,730 equals the initial amount at the moment of death, which is 100%, times E raised to the half-life times K. We have this 5,730 because that is our input for T. Now, since this is the half-life, that means the original amount divided by 2 is the half-life. That is equal to this expression at the right. Let's remove this expression at the left. So what we now have is the amount of carbon-14 after 5,730 years, which is the half-life, which can be represented as 1/2 of A, or A over 2, is equal to A times E raised to the year 5,730 times certain constant. Now, our problem here is we do not know the value of K. So the first thing that we have to do is we will compute first for the value of K. Notice here that A and A are common. So what we can do is we can divide by A, we can divide by A. Therefore, we can cancel out the A. We have here 1. So we have 1/2. And then this A is canceled out. So we are left with E raised to this exponent. Now, from 1/2 equals E raised to 5,730k, since you have here a number, E raised to an exponent, we can simplify this by taking the logarithms of both sides. And since our base is E here, then we can get the natural logarithm of both sides. So we have ln of 1/2 equals ln of this expression. Now, I write 0.5 instead of 1/2 to conserve some space. Recall the property of logarithm. It says the logarithm of m raised to p is equal to p times log m. It's just like putting this p at the start. Now, why does this work? Remember that log to the base b of m is an exponent. This is an exponent. And if you have an exponent raised to another exponent, we can apply the power of power. Concretely, if you have x to the second, all raised to the third, we can simplify this by multiplying 3 times 2 to get x to the 2 times 3 is 6. Now, this log to the base b of m, you can think of that as this exponent and this p as the other exponent. When you simplify this, you are going to multiply this 2 times 3 to get 6. So multiplying p times this base is now the same as p times this log to the base b of m. That's the reason why we have this property. And by applying that here, then we can put this exponent to the front to get 5,730k times ln of e. And then here you have ln of e. What's the value of ln of e? ln of e is equal to, let's say, certain number x. This is equivalent to saying the logarithm to the base e of e is equal to x. And by writing this in exponential form, what we have is the base e raised to this exponent x is equal to this number e. So therefore, the value of ln e is 1. And then dividing both sides by 5,730, we got this expression for k. ln of 0.5 divided by 5,730. Using your calculator, you can compute ln of 0.5 and divide it by 5,730, and you will get the value of k. So the value now of k is negative 0.00012. you have a negative sign here because what we have is a decay. We need this value of K so that we can model the exponential decay of carbon-14. From our formula for continuous decay, we now have this decay function for carbon-14. So this function now is our specific model for the decay of carbon-14. And we are going to apply this to solve our problem. So in our problem, we are given an animal bone that contains 2% of carbon-14, and we are asked to find what is the age of that bone. So using now our model for the carbon-14 decay function, we now have f of t to be 2% of the original amount. The initial amount is A, so we have here 0.02 A, which is the same as saying 2% of the initial carbon at the time of death equals 100% of that initial amount, E raised to our constant that we just derived times T. We are solving for this variable T. Notice here that A and A are common, so we can cancel this out to get 0.02 equals E raised to this exponent. And since we are solving for T, which is in the exponent, we can get the logarithms of both sides. Since the base is E, then we get the natural logarithm of both sides. So we now have ln of 0.02 equals ln of E raised to this exponent. And then applying the property of logarithm, we can write this exponent as a factor in the front. We just copy the left side. And then we know from the previous slides that ln of E is 1. So what we are left at the right side is just this negative 0.00012t. We just copy the left side. And then we can divide both sides by this factor so we can compute t. So we now have ln of 0.02 divided by our value of k equals t. And that gives us a value of t of 32,600 years to be the approximate age of our fossil. To check, you can substitute f of 32,600 equals AE raised to negative 0.00012t. But at the moment of death, we have 100% of all the carbon-14, so we have 1 here, and we substitute t to be 32,600, and you will get a value of approximately 0.02 or 2%. Now, the second part of the problem is, if prior research points that the animal being around 20,000 years old, how much carbon-14 should be in the animal? So by applying now our model for carbon-14 decay, we have f of 20,000 years equals the initial amount, which is 100% at the start, times E raised to the k value of negative 0.00012 times 20,000 years. Then simplifying this right side, we have E raised to negative 2.4. And then solving for E, we got a value of about 9%. So an animal that is 20,000 years old is expected to have about 9% of its carbon-14 present in that animal fossil. So that's the beauty of Dr. Libby's creation, this radiocarbon dating. And if you find this concept beautiful and useful, we have Dr. Willard Libby to thank for. Thank you very much.